Hello and welcome to another Just Enough Computer Science episode when we are finally going to actually start building our computer. Just before we do, let me show you the baseboard in its final form, at least for this computer. Sorry. Now then, you can see we've got these breadboards all set up. You can see we've got a couple of sets of bus rails coming down. You can see I've linked them up with wires, slightly different coloured wires. All of that will be explained in later episodes. You can also see I've linked all of the power rails on both sides. And you might think, well, why do you want to link them on both sides with the power supply coming in the middle? That seems a bit overkill. Well, the thing is, you get all sorts of little sort of anomalies in the voltage, especially when you get lots and lots of different components all interacting with each other, and you get little bits of things called inductance, where these wires create tiny magnetic fields which interfere with the signals. And the problem is, the signals is pretty much the only thing we're interested in electronics. So you can get spurious results and all sorts of dodgy things. So you need to have as many power rails as we can reasonably have. We don't want to push the power too far. And you might be able to see these little brown things. And these little brown things, which are going across the power rails, are called capacitors. So let's have a brief think about capacitors and what they do, because it's going to become relevant in a minute. So, capacitors. Capacitors, in this context, are connected between our power rails. So we've got positive up here and ground down here. And we connect the capacitors across them. And it's all right, we're normally told not to connect components directly between the voltage and ground. But it's all right because actually, ultimately, no current really flows through a capacitor. What a capacitor is a tiny little battery. So it will charge up until it's the same voltage as that, and then it won't allow any more current through. So it's sort of all charged up. And the effect of that is that, let's say, your voltage should be a nice steady voltage like that, okay? But it isn't. Your voltage will be doing that. Okay, it'll be going up and down, and it'll be all noisy. And when the voltage is high, too high, a capacitor will swallow some of the charge and bring it back down. And when the voltage is too low, it'll spit out some of the charge and it will push it back up. So it'll, instead of having this horrible sort of jaggedy signal like that, it will do this. It will sort of smooth it out. And so all the lumps and bumps get smoothed out. The reason why I've got so many of them is that at various different points on the circuit, different components may well start interfering with the smooth running of the circuit. So I'll have as many capacitors as you possibly can. Now we're going to use capacitors for a slightly, well, for the same reason, but for a slightly different purpose in a minute. Because one of the things that a computer needs is a clock. A clock is not something that tells the time. It's simply something that goes tick tock, tick tock. And in this context, it's sort of low voltage, high voltage, low voltage, high voltage, low voltage, high voltage, like that. Okay, and the reason is that the processor is going to receive information, it's going to throw out information, it's going to do calculations, it's going to do all sorts of things, and it needs to know when to do them. So every time the clock goes high, here, 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 that's the processor signal to do the next thing, to look for the next piece of data, to spit out the last piece of data, whatever it's going to do, that's its signal. This is called the rising edge of the clock. And you might think, well, that is relatively simple to arrange, and it is. You can, for example, get something like this. This is a crystal oscillator. This is the one we would, in fact, eventually be using. And you just put electricity across it, and it buzzes up and down. But it produces a clock signal, this particular one, of 1 megahertz. That is to say, 1 million times every second. So that's great when we want the computer to run as fast as we possibly can. Although I should point out that 1 megahertz is incredibly slow by today's computer standards. A modern computer by today will run many thousands of times faster than that. But nevertheless, when we are just starting out and working out what's happening to our computer, we don't want it to happen a million times a second. That's far too fast for us to see. We want it to happen really slowly, possibly even like once a second. And by that point, you may as well just get a button and push it. So we go high, low, high, low, high, low. So we can, it's called stepping. Okay, so we can just step through our processor and what it's doing, one button push at a time. And you might think that would be very simple. Okay, here we are. Here is our voltage. Here's our ground. And we did this before, okay? We can just simply get a resistor and a switch like that. Okay, and every time we close the switch, the signal will go low. And then when we open the switch, the signal will go high. And we can just push the button. And yeah, that is true. That's worked perfectly well on our previous circuits, just like that, no worries. The trouble is that switches bounce, by which I mean when you push them closed, they don't absolutely close the millisecond you push them. The little pieces of metal inside bounce up and down fractionally. Now, very, very fast, far too fast for the human eye to see, but not so slow that or not so fast that a pro computer can't pick it up. So that's a bit of a problem. However, what we can do, if we add another little resistor in and put in a capacitor, which is what we were using to smooth the power, then that should help. So if we have a look at this, instead of on a bouncy switch, it's going to go high, low, high, low, high, low, high, low, high, then okay, and then low, high, low, high, low, high, low, low, okay, and you're going to get this noise at the beginning at the edge, and it might very well trigger extra clock cycles that you don't want. Well, with a capacitor in place, what it will do is it will go high, bouncy, 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 high, low, bouncy, 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 low, high, bouncy, 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 high, and so on, okay, and maybe that's good enough. But the trouble is that, let's say your processor is triggered in the middle somewhere. If one of these bounces accidentally gets above there, it can trigger an extra clock cycle. And if one of these bounces accidentally goes down a bit, it might also trigger an extra clock cycle. So in here, our final bit is we're going to have one of these. And you might have seen this before in one of our previous videos. It is just a NOT gate, but it's not any old NOT gate. Specifically, it is a NOT gate with a Schmitt trigger. Okay, a NOT gate with a Schmitt trigger, which sounds a little bit strange, so let me explain. So normally, here's a signal, here it is high, and here it is low. Okay, normally, you would expect the input just to have a look somewhere in the middle. And when it's higher than that, it's high, and when it's lower than that, it's low. And as we said, if you get bounciness, you can sometimes trigger it when you're not expecting it. Well, a Schmitt trigger doesn't work like that. A Schmitt trigger has got two voltages that it looks at. High-ish and low-ish. So, when the signal goes below this line for the first time, it goes low, and it can bounce around all you like. It doesn't matter, it's staying low. And it won't go high again until it goes above this upper signal. So it can bounce around all you like, but it's going to stay high. Okay, so this thing is actually, it's called hysteresis. It's when you separate the thresholds, okay, such that it will only go low when it goes below a particular number, and it will only go high when it goes higher than a higher particular number. It's the way a thermostat works in your house. Otherwise, if your thermostat was constantly switching on and off, it would around and about the temperature that you wanted, it would wear out all of your central heating system. So this is what we want. We want a Schmitt trigger. And fortunately, we have one. We have the 74HC14, okay, which is not one of the ones that we looked at. I think, let's have a look at the ones we looked at. The NOT gate that we looked at was the 74HC04, which is just a normal trigger, but normal input. But this one specifically has a Schmidt trigger. So if I go back to my circuit here, you can see that I've actually, the way I've got it set up here, this will be connected to high unless you push the switch, at which point it will be connected to low, which is sort of the wrong way around. You want it to be off until you push it and then it's on. This is on until you push it and it's off. But because we're pushing it through a Schmidt trigger, which is an inverter, it is going to be the right way around. And then what we'll do is we'll put an LED at this end to check to see if it's working. So I suppose we better go and build that, hadn't we? Let's do that now. Okay, so when we put this circuit together, it looks like this. Okay, here we've got the resistor coming down to a switch here, which then goes down to ground there. We've got the resistor coming out of the switch with the capacitor going down to ground there. Okay, it then goes into the Schmidt trigger, which actually we've got it coming out here, out the front here, which we're just going to connect it to a little blue LED, and you can see we've got the power supply on the chip as well, which should mean that what we have is a really overly complicated button which lights an LED, but it is debounced. Now, the purpose of a clock is to trigger the processor to do something, and indeed other components sometimes in the circuit as well. So the processor is going to be here, so we could just run the clock signal over here, but also what I'm going to do is, if you have a look down the sides here, one of these power rails has got a little white cable on it. I'm going to use white for clock, so I'm actually going to run one signal from the clock pin over to that rail, and then I can pull the clock signal off at any point down this whole circuit, and that will mean that I always know where the clock signal is. For those of you who know anything at all about computer science, I'm sure you will have guessed what these other, they're called buses, are for, but we're going to talk about that another time when we've installed our processor, which is the job for the next episode. So I shall see you then. Goodbye.